Good morning. I'd like to spend the next few minutes with you discussing the results of a study we're conducting that compares the host response to different biomaterials that are used in spine surgery. And the reason that the host response, as I refer to it, is important is iterated here by Jim Anderson. He states that the primary determinant of success of any biomaterial is the host response, which seems rather intuitive. But unfortunately, the host response is one of the last design considerations that's thought of in the development of biomaterials, especially in load-bearing applications, where one is more concerned about how strong it is and whether it's degradable and porosity and factors like that. In order to appreciate the importance of the host response, it's necessary to understand the significant advances in our understanding of the immune system, or basically immunology on the whole, over the past 20 years. This probably is among the top 5 most significant advancements in medicine because of its far-reaching implications and applications. But the immune system, which was thought to be pretty much exclusively exist to defend us against pathogens, bacteria and viruses and so forth. Now it's known that it's not just important, but it's absolutely essential for normal fetal development, for the maintenance of a normal homeostatic healthy state of all tissues, regeneration of certain tissues following injury, and of course the host response to biomaterials. So let me just spend a second here discussing this with you. Look at this diagram where macrophage heterogeneity is described. That M0 is the monocyte we know about in the peripheral blood that leaves the bloodstream, goes into the tissues, becomes a macrophage. And if you look on the left side there where it says M1, that's a pro-inflammatory macrophage. Just as we've always learned, it's a killer cell. It secretes a bunch of cytokines and chemokines meant to promote inflammation and kill bad things. What we did not know until 20 years ago was that a cell that same precursor mononuclear cell can become an identical looking macrophage that does almost exactly the opposite. It's anti-inflammatory, secretes an entirely different profile of cytokines and chemokines, and is responsible for resolution or ending of inflammation. And this is really critical. And the reason, of course, we didn't know that up until 20 years ago is because they look identical, but we can identify them by certain surface markers. This slide is just a different way of looking at the same thing from the left, the monocyte differentiating into different phenotypes of macrophages. Now, in reality, though, it's not one or the other, pro-inflammatory or anti-inflammatory. It's a spectrum of macrophage phenotypes that is dependent upon the environment in which macrophages find themselves. So in the context of biomaterials, the reason that becomes important is because the environment includes the surface of the biomaterial, degradation products, and so forth. We conducted a study about 15 years ago that has probably been cited as much as anything that we've ever done. We looked at about 20 different biomaterials, most of them naturally occurring biomaterials, and we implanted them in a well-defined animal model and a priori established criteria to say this is a good outcome or a bad outcome. The tissue from each animal was examined by 5 blinded reviewers who scored them, and if you look at the top part of this graph here, those 2 histograms on the left, the lower the score, the worse the outcome, and the higher the score, the better the outcome at 14 days and at 35 days. And the good news was that this scoring result ended up being almost an excellent correlation with clinical use. The materials on the left weren't even used anymore. Many of them were off the market, and the others on the right had the huge market share. If we then take those same slides and look for the phenotype of the macrophages and generally classify them as in the ratio of M2 to M1, in other words, anti-inflammatory to pro-inflammatory, you can see we've got now a really nice correlation between the higher the M2 types, the M2 to M1 score, the better the clinical outcome. And in the present study design, we took that same concept. We take mononuclear cells from the bone marrow of mice, turn them into macrophages, and expose different materials to them, and then we characterize their phenotype. And this next slide shows you what happens in the controls. F480 is a macrophage marker. We can turn them into a pro-inflammatory cell that stains positive for INOS in that second row, and they light up green, and they still show the macrophage marker. Similarly, we get the Fis1 anti-inflammatory marker. And if we take a naturally occurring material like small intestinal submucosa, degrade it, expose these cells to it, we get an M2 phenotype. If we take this ECM, the extracellular matrix from bladder, muscle, spinal cord, brain, esophagus, every single extracellular matrix transitions these cells into a favorable, constructive, remodeling type of a macrophage phenotype that are associated with good clinical outcomes. Now, if we do this same assay and we expose two materials, Z-Fuse and PEAK, to the same in the same macrophage assay, you can see circled in red there that the Z-Fuse transitions macrophages to an anti-inflammatory phenotype, whereas PEAK does not. If we take that assay a step further, where we first make the macrophage a pro-inflammatory type, then expose the cells to the same two biomaterials, you can see that we now also get the Z-Fuse will suppress the pro-inflammatory response and promote an anti-inflammatory response, where PEAK does not. So there's something different about these two materials that gives an opposite response, induces an opposite response in macrophages. If we start looking at some of the specific markers, over on the left, arginase is an anti-inflammatory marker. You can see that even though it's not statistically significant, we get a trend towards Z-Fuse showing more amounts of arginase production by the macrophages. INOS is a positive marker, and you can see that, again, there's no statistical significance, but we're getting a trend towards suppression of the pro-inflammatory marker. We do have a statistically significant difference in another anti-inflammatory marker, Fis, where Z-Fuse induces not a greater amount of it, not only compared to PEAK, but also compared to titanium. If we look at two pro-inflammatory markers, IL-1 beta and IL-6, we can see there, surrounded by red, that we get a greater induction of the pro-inflammatory phenotype by titanium compared to either PEAK or Z-Fuse. So these materials definitely cause different types of phenotypes and host responses in the patients. Now, the one important question in the spine, obviously, is what does that do with osteoblastic activity? And from a general standpoint, anti-inflammatory phenotypes promote greater osteoblastic potential. Because of the COVID-related restrictions over the past 6 months, we've been unable to complete this study yet. We're back in the lab doing this now, but all of our results to date show that we have a greater osteoblastic activity for Z-Fuse compared to either PEAK or titanium. So in conclusion, considering the host response in the early design and R&D phase materials is going to improve downstream outcomes. And the other conclusion of the present study is that Z-Fuse promotes a pro-remodeling, anti-inflammatory host response. I want to thank you very much for your attention.